mil. Simulation programs have been developed for the MMPP model as described before. Here are the parameters that we will use in the simulation program. In order to prevent excessive jitters, we will define a system voice packet delay requirement. That is the probability that the delay is less than or equals to 50 milliseconds is greater than or equals to 0.95. So we will define the system voice over IP capacity as the maximum number of voice collections that can be supported while the packet delay requirement can be fulfilled. We have tried to vary the mean handoff processing time to see how this will affect the system voice over IP capacity. This graph shows the result. If the mean handoff processing times increase, the system voice over IP capacity will decrease. This is because when the mean handoff processing times increase, the portions of the time that the server needs to stay at the off state will be higher. So, the voice packet delay will increase, and the number of voice over IP supported will decrease in order to keep fulfilling the system packet delay requirement. When the mean processing time is 0.06 seconds, the number of voice over IP that can be supported will be 18. In this case, the duty cycle for processing handoff requests was about 4.5%, but the reductions in the system voice over IP capacity was 41.9% when compared with 31 voice over IP collections in the case without handoff event. We have also varied the handoff frequency to see its effect on the system voice over IP capacity. The result is shown in this graph. When the handoff frequency increases, the system voice over IP capacity will decrease. This is because when the handoff frequency increases, the chance for the server to be at the off state will increase. So, more voice packets will be delayed, and the number of voice over IP supported will decrease if the system voice packet delay requirements is unchanged. When the handoff frequency for a single voice over IP collection is 0.04 per second, the number of voice over IP collection that can be supported is 25. In this case, the duty cycle for processing handoff requests is about 4%, but the reduction in the system voice over IP capacity is about 90%. We have also tried the case when there is no handoff message. In this case, the number of voice collections supported is about 31. When there is handoff control message present, we assume the mean service time for the handoff request is about 40 milliseconds. The number of supported collections reduced to 24. In this case, the duty cycle for processing handoff requests, that is the portion of times that the server is serving the handoff request, is about 4% only. But the reductions in the number of collections supported could be 23%. Actually, the developed models can be used for optimizing the threshold values to start the handoff process in different handoff schemes. Since the threshold will affect when the handoff stations will start its handoff process, it can affect the system handoff frequency and also system voice over IP capacity that can be supported as shown in our analysis. At the same time, this threshold may also affect how far the handoff stations will be from its previous AP when it starts the handoff process. These separations can affect the handoff scheme successful probability. So, there will be a number of different parameters that can be optimized by these threshold values, and this will be the further work for our analysis. In conclusion, we have carried out an analysis to see how the handoff control messages will affect the voice packet delay in the system. The result shows that voice over IP capacity was reduced by 23% when the duty cycle for processing handoff requests was 4%. And this model will be useful for optimizing the parameter settings in different handoff schemes. This is the end of my presentation. Thank you.